A very good morning to all of those who are, who are watching these lectures, and to those who may watch these lectures uh, uh, based on quantum mechanics. And today, as you know that in the last video, what we did, we talked about variational principle, and we talked about the implications of variational principle, and we tried to explore the validity of variational principle in the domain of classical physics, uh, where we have uh, Hamilton's principle of least action acting as variational principle, uh, leading to leading to the equations of motion via Lagrangian and Hamiltonian. And then we talked about the variational principle in quantum mechanics, and deliberately I have been trying to explore this variational principle to the problems which are exactly solved using preliminary quantum mechanical principles. And in the very first case, what we did is we chose the problem of hydrogen atom, and we used variational principle to explore the problem of hydrogen atom in ground state, and we exactly know that we finally came up with the energy eigenvalues of ground state of hydrogen atom using variational principle. Now, I want to give the same kind of formulation to the harmonic oscillator problem, and certainly I will use a variational principle to solve the already solved problem using preliminary quantum mechanics. That's the ground state of the harmonic oscillator. Now, before proceeding into the variational principle using the variational methods, we can also call them as variational methods, to explore out the ground state energy of this harmonic oscillator. It's better to start with what a harmonic oscillator basically is. And if we have to define a harmonic oscillator, you have anything which has any kind of action which tends to regain its original position, leads to an oscillation, and this oscillation is referred as harmonic oscillation. So in case of this harmonic oscillator, what it does basically, it exhibits a restoring force. You apply a force, and there is a restoring force, and this restoring force is directly proportional to the displacement. Appearing such kind of harmonic oscillator quite consistently appearing in mechanical and electrical systems, and as an ideal harmonic oscillator in quantum system. So talking about the classical harmonic oscillators, we have the problems like the spring problem, where you will hang on a spring, you will apply some force, and the spring is going to oscillate with respect to some main position. And the oscillations that will be set up in the spring leads to what we call as harmonic oscillations. And so this mass spring, it simply acts as a harmonic oscillator. And then the next one that we have is the simple pendulum. We have a pendulum watch, okay, and the pendulum oscillates with respect to some main position, and the motion that's executed by pendulum is a harmonic oscillation. And a pendulum, a simple pendulum, is a harmonic oscillator. And then we have some machineries and where we have the vibrations And these vibrations can also be attributed to what is called as harmonic oscillations, and and the disturbances that are happening beneath the planet, and the disturbances, if their nature is periodic, uh, uh, that periodic nature of the disturbances, what we call as seismic wave wave modeling. Now these waves, they also have the oscillatory motion. In general, if we take on any classical system, uh, uh, it has the existence of harmonic oscillators. If we boil down our problem of understanding to the atoms and molecules, uh, at room temperatures, these atoms and molecules are oscillating. So if they are oscillating, they all have oscillatory motions. These all microscopic particles are executing the harmonic oscillation type of the motion. So you cannot imagine basically anything in quantum systems where you will not have a situation of harmonic oscillation. Even if we go close to the absolute zero. And these harmonic oscillators, they have tremendous applications as long as the classical harmonic oscillators are concerned. And you can build the shock absorbers in vehicles by understanding the oscillations. You can build clocks with the pendulums that can give us the time, and all the structures that we basically build in world, from buses to buildings, you have to take into account the oscillatory setup of these buildings and oscillatory setup of these buses and cars, because without analyzing and without making calculations on oscillatory motion of these objects, we cannot expect a structure to be stable for a long time. So that is the role of engineering that plays in building these clocks, bridges, and buildings based on this oscillatory motion. And we have its applications in electrical circuits. If we rightly go back 20, 30 years, the radios and they all worked on the principle where an LC circuit making an oscillation and resonating with the oscillations of the electromagnetic waves that are coming from antennas and leading to that resonance and giving us the particular station in our radio systems. So they have applications in all technological aspects that we have in the modern world, from mobile phones to internet devices, to the televisions and all that. And then they have a very good application as quartz oscillators that we make use in voice. And as I said, the resonant circuits, there you have the application of these electrical, of these harmonic oscillators that work on the basic principles of the classical physics. Now, talking about a harmonic oscillator based on quantum mechanics. Now, in quantum mechanics, what we have is the harmonic oscillator. It describes the systems where the energy levels are quantized. And this is basically a fundamental in the quantum field theory and the field of spectroscopy. So this is the domain of the quantum mechanics where the harmonic oscillator problem is plausibly executed. It's plausibly used to understand the systems where we come up and describe the systems with quantized energies, which is not the case when we talk about the classical harmonic oscillators. The energy of a classical harmonic oscillator is continuous. It is continuous at all points, but that's not the case when you schedule this problem at the quantum mechanical level, taking a particle, a quantum particle, as a harmonic oscillator. And when we describe this harmonic oscillator, we come up with the results telling us that this harmonic oscillator does not have continuous energy. It has the quantized form of energies, and this certainly becomes a basis for quantum field theory and spectroscopic analysis. Talking about the applications of this quantum harmonic oscillator, it has drastic applications in understanding the molecular vibrations in spectroscopy, in understanding the quantum dots. When you break down a solid to a nano state where the classical physics does not work, the harmonic oscillator plays an important role to understand these quantum dots and these nanostructures. And then we have the problem of phonons. If we go into the domain of superconductors, as we know that a superconductor is a material which does not offer any resistance to the flow of current. So we can basically explain the phenomenon like Cooper-Pire tunneling in a superconductor, and that Cooper-Pire tunneling in a superconductor is basically mediated. The formation of a Cooper-Pire is basically mediated by the phonons, and treating phonons can be a very good way of understanding the condensed matter physics, and ultimately leading our understanding to understand the quantum optics and light interactions, the interaction of light with microscopic particles. So these are some of the important applications of harmonic oscillator. And so to conclude this introduction, for classical harmonic oscillator, what we have the continuous energy, and classical oscillator is its motion is completely deterministic, and determine its motion completely. And talking about the quantum harmonic oscillator, what we observe is the discrete energy levels, and obviously the probabilistic wave functions that we deal in quantum. So both the classical and quantum oscillators, they share the same mathematical foundation, the basic mathematical foundation of a classical harmonic oscillator and the quantum mechanical harmonic oscillator. That has to be same, but they differ in interpretations and applications, because the classical harmonic oscillator, for that you have to start with the Newton's second law of motion. However, when we talk about the quantum harmonic oscillator, here we start with what is called as Schrodinger's wave equation. So I can say that this classical harmonic oscillator, they have engineering applications, but at the same time, the quantum harmonic oscillators, they're basically crucial in understanding the nature of the reality. We want to understand the quantum nature of the harmonic oscillator, because we want to understand the nature, and certainly they are crucial in modern physics, explaining the molecular and atomic behavior, subatomic behavior, and the behavior below the subatomic particles. So this was a brief introduction. I was just trying to introduce the problem of harmonic oscillator, and treating the two frameworks, the classical framework and the quantum mechanical framework. And we are in the domain of quantum mechanical framework, uh, and what we want is we want to use a variational principle. Basically, we want to use variational principle to this problem of harmonic oscillator. And as I said, that using preliminary quantum mechanics, we solve the problem of ideal harmonic oscillator, and we obtain its ground state energy, first state energy, and first excited state energy. So we are using variational approach to a problem which is already solved in order to understand the applicability of the variational principle. So what we have here is we want to discuss the ground. We want to discuss the ground state of the ground state energy of harmonic oscillator. This is our target, and we want to work on it. And so what is so simple about this problem is that we already can guess the nature of the trial wave function, because we have already talked about the calculation of the ground state energy, and this ground state energy is the expectation value of a trial wave function and acting on the system and assuming that the trial wave function is normalized. So this is how we calculate the expectation value of the ground state energy of a system. Now, in our context, what we have is we have the problem of harmonic oscillator. And if we have a problem of harmonic oscillator, we can purely guess the nature of a trial wave function, and we can start with that trial wave function and use the variational principle, because once we calculate this, we calculate delta Eg equals 0, then obtain the adjustable constant, the value of the adjustable constant, and in doing so, what we do is we calculate the ground state energy of the harmonic oscillator. So what we have now basically is we have to start with a state vector. We have to start with a wave function. If I take my trial wave function, so trial wave function, so let me assume this function to be the ket of psi equals ae to the power of minus beta x square. So assuming this to be the trial wave function, since I'm talking about the ground state of the harmonic oscillator, then there should not exist any node. Now, what we have node, and the opposite of the node is antinode. Now, what is a node? A node is a point where the probability of getting the wave function, where the probability of getting this eigenfunction equal to 0 leads to a node, and the probability of getting the maximum value of this eigenfunction leads to what is called as antinode. So our trial wave function should be such that when we are talking about the calculations of the ground state of the harmonic oscillator, in this case we don't have a node, so the trial wave function should be, first of all, it should be an even function. It should be an even function. And we can see from this trial wave function, if I replace this x by negative of x, the overall shape of the equation is not going to change. So replacing this x by minus x will not change this function, will not change this trial wave function. So this function is an even function. So it has to be an even function and it has to be symmetric. And it must be an even function, it must be symmetric, and there should not exist any node in the trial wave function. So how can we verify that the function that I have chosen here, the state vector that I have chosen here, does not carry a node? So for that, this function which I have chosen, a e to the power of minus beta x squared, this must be equal to 0. Now what we can see here is this a is a normalization constant. So the value of this a is not equal to 0. If the value of this a is not equal to 0, that means this e to the power of minus beta x squared, its value must be equal to 0. Now the question is that what are those points where the value of this exponential function can be 0? This is an exponential function and this function has the finite value. But its value goes to 0 only if x is equal to plus infinity or x is equal to minus infinity. And we can easily see this. If x is going to plus minus infinity, under both these cases, the value of this exponential function will lead to 0. So at those points, the value of the eigenfunction psi will be equal to 0. The value of the eigenfunction will be 0. So what we can conclude from this is we have verified that the trial wave function that we have chosen here, this is an even function. The next important thing is that this function does not carry any nodes. So if this function does not carry any nodes, then certainly it has everything to do, it has everything to be the part of the trial wave function that I have chosen to solve the problem of the harmonic oscillator. So this thing is clear, and now let's go on using variational principle to calculate the ground state energy of this harmonic oscillator. Now, for harmonic oscillator, what we have the Hamiltonian operator, and what is that? That is minus h bar squared by 2n. Since we have chosen a one-dimensional harmonic oscillator, so here we will be using the total derivative d2 by dx2, and then the potential energy part will be 1 by 2 and omega square and x square. So here what we have is this is our operator, and this x is also an operator, and we know that when we execute a position operator on an eigenstate, we come up with the position of that operator. So this is my Hamiltonian operator for the harmonic oscillator. This omega is the angular frequency, because when you have oscillations, you have the frequency, then you have the angular frequency, and you have the displacement. So if you think of a harmonic oscillation, what it does have, it has a displacement, and that displacement has the relation with the mean position of that harmonic oscillator. So this part takes care of kinetic energy of this ideal harmonic oscillator, and this part takes care of the potential energy of the harmonic oscillator. Now, what is the first thing that we are supposed to do at this stage? The first thing that we are supposed to do is to calculate the normalization constant. Calculate the normalization constant. Okay, so in my case that is A, and for that I have to use the condition of normalization. So I have to calculate the inner product of psi with psi. So this will lead to the integral from minus infinity to infinity, a e to the power of minus beta x squared, then again a e to the power of minus beta x squared, then you have dx is equal to 1. Because as we know that when we have to calculate the normalization constant, we use the condition of normalization. So we have used the condition of normalization here, and we want to calculate this constant a. So what will come out of this is a squared will be out, then you will have minus infinity to infinity, then you will have e to the power of minus 2 beta x squared dx is equal to 1. Now, what we have is we have an integral, and this integral has a value, and what is its value? It is, this integral is, if we have an integral from minus infinity to infinity, e to the power of minus alpha x squared dx, its value is under root of pi by alpha. So we can use the value of this integral in our equation. So instead of alpha, we have to beta. So the integral minus infinity to infinity e to the power of minus 2 beta x squared dx will give us under root of pi by 2 beta. So I can use that here. So this is a squared times under root of pi by 2 beta is equal to 1. So we can transfer these constants, and we can get the value of the normalization constant. So we will have a squared is equal to under root of 2 beta by pi. So if I have to write down a, so it will be 2 beta by pi. This is whole raised power 1 by 2. Then you have the whole raised power 1 by 2. So the value of this normalization constant is it is 2 beta by a. It has to be the pi raised power 1 by 4. So this is the value of the normalization constant. So now what we have to do is we have to calculate the expectation value of the energy. And because we want to calculate the ground state energy of this harmonic oscillator, so how can we do that? We can do that by writing down the ground state energy as the expectation value of the Hamiltonian acting on these island states. So this is our Hamiltonian operator here. Now I can write down this as psi. For Hamiltonian it is minus h bar squared by 2m. Then you have d2 by dx2. And then for potential energy what we have is 1 by 2 m omega square x square. Now x is an operator. And then I'll close it. So we can divide this this bracket into two brackets, and for that I will have the bracket 1 as psi minus h bar squared by 2n d2 by dx2, and then I will have psi for it, and then plus psi, and then this part will be 1 by 2 and omega square x square psi. Now what we have to do is we have to solve these two brackets, and that will give us the expectation value of this ground state energy of this harmonic oscillator. So for this part I have an integral, for this part I have an integral, and this integral will certainly extend from minus infinity to plus infinity. So in the first case I will have, so what I have is Eg. So what I have is I have an integral ranging from minus infinity to infinity. Then I have a e to the power of minus beta x squared. And then I have d2 upon dx2. Then again I have a e to the power of minus beta x squared. And this part will be multiplied by its own dx. And then plus, the other part is integral minus infinity to infinity. There we have again a e to the power of minus beta x squared. And then we have 1 by 2m omega squared x cap squared. And then again a e to the power of minus beta x squared dx. This is the story till now, and what we can do here is this a and a will give us a squared, and then we will have integral minus infinity to infinity, and then e to the power of minus beta x squared. I can keep it like this. So I will take the first derivative of this exponential function, that is e to the power of minus beta x squared. So the internal derivative of this exponential will give us minus 2 beta x. It has to be like this. And the exponential function will remain as it's e to the power of minus beta x squared. And then I will close it for this step. And then here plus I will have again a square out, and 2 will be out, and then m omega square will be out. So inside the integral what I will have is minus infinity to infinity, and I will have x square e to the power of, they will make the 2, this is minus 2 beta x square dx. Okay, so we will have to proceed from here to solve these parts of these integrals. So let's move on from here. Now what we can see here is we can see that that I have to take another derivative of this, because I have taken just one. I have to take another derivative. Okay, I've done it wrong. So this has to be, come on, this has to be 2 beta x e to the power of minus beta x squared, then close it. Now I have to take another derivative of this thing. Now I have two functions, and in the first derivative, when I took the first derivative, I had one exponential function, but now I have two functions. So in order to take another derivative, I have to make the UV rule here. I have to make use of the UV rule of differentiation. Now let's proceed from here. So what I'll have is I have a square, and then I have integral minus infinity to infinity, and I think this minus 2 beta will be out. Okay, and then we will have x e to the power of minus beta x. I have to take its derivative. Now d for derivative dx, and then the next term that we have is plus a square by 2m omega square, then the integral minus infinity to infinity x square e to the power of minus 2 beta x squared dx. Now this is it. So I have to take another derivative of this. I'm not sure whether this is only a square from the other side. So So let's move on from here and see if we can reach out somewhere. So what is out here is a square to beta. The negative sign is out. Now let's differentiate this. So we have the integral from minus infinity to infinity. So u as x, so x as x, into the differentiation of this will give us, this has to be square here, minus 2 beta x e to the power of minus beta x squared plus v as x, that is e to the power of minus beta x squared as x, into the differentiation of the x, and differentiation of x will give us 1. So now I have to close it. Okay, I'll close it. So this is dx, and then we have the same thing as is written here. It's a squared m omega squared by 2. Then I have integral minus infinity to infinity x squared e to the power of minus 2 beta x squared dx. Okay, so what we are left here with, so now we have 3 integrals. This is integral 1, then we'll have another integral, then we have the third integral coming out of this. So let's write down those integrals. So if I do that, what will I get here is this minus and minus will make it plus. So this will be 4 beta a squared, then integral minus infinity to infinity. Then this x and x will give me x squared e to the power of minus beta x squared dx. Okay, this will be 1. Okay, I think I'll use the new page. Let's go with that. So what I'll have 4 beta a squared. 4 beta a squared integral minus infinity to infinity x squared e to the power of minus 2. Is it 2 or only beta? It's beta. Minus beta x squared dx. So this will be term number 1. The term number 2 will be, again, it will be 2 beta a squared, but minus. Now it will be minus 2 beta a squared integral minus infinity to infinity e to the power of minus beta x squared dx. Come on. And then I'll have to check that. Okay, so something is happened absolutely wrong. I have missed something absolutely, and what's that? I think that is, okay, yeah, I have not multiplied this differentiated part with e to the power of minus beta squared. So we have to multiply it with e to the power of minus beta squared. When we will do that, this will become 2 times. This will become 2 times beta x squared, and this is also 2 times beta x squared, and the last term that we will have is plus a squared m omega squared by 2, and integral minus infinity to infinity, then again x squared e to the power minus 2 beta x squared dx. Now look at this. Now look at this. What we have achieved till now is we have 3 integrals, and 2 of the integrals are exactly same, and this integral is different. Okay, and I think everything else is fine now. Nothing wrong with it. So we would like to write down the values of these integrals. So in doing so, what we have is we have integral minus infinity to infinity x raised to the power 2n e to the power of minus alpha x squared dx. For this you could write down the value of this integral is 1.3.5.2n minus 1. 2n minus 1 is the last term, divided by 2 alpha raised to power n under root of pi by 8. So from this integral, we can use the value of n equal to 1, and I can calculate integral minus infinity to infinity as x raised to power 2 e to the power of minus alpha x squared dx. So for using n is equal to 1, I'll get 2n minus 1. So the first term I have to take for this integral. So the first term that I will have is 1 by 2 alpha under root of pi by a. Now in our problem, instead of alpha, we have minus 2 beta. This is alpha here. This is alpha for this problem. So I'll have 1 by 4 beta under root of pi by 2 beta. So this will be the value of the integral that we have to use for these two integrations. Okay, and this one is already known. Its value is under root of pi by alpha. So instead of alpha, we will have to use 2 beta. So proceeding from here, what we'll get. So what should I do is I will be replacing this integral. I'll be replacing this integral by its value. And what is its value? Its value is 1 by 4 beta under root of pi by 2 beta. Okay, this is the value of this integral. So the same thing will be used here, because this is the same kind of integral that we have, and we can use the same situation here. So here what we'll have 1 by 4 beta under root of pi by 2 beta. And then for this integral, I'll be simply using the value. What is that? That is under root of pi by 2 beta. So you can see we have boiled down this problem to the simple numbers now. And all we have to do is to use the value of a square. And a square is already calculated using normalization constant. And you can calculate this a square. You can use this a square in all of these terms, and finally you will achieve the result. And I will put this part in your hands. You will be solving this part of the problem. All you have to do is to use the value of a square and then make all the cancellations and get the final energy of this harmonic oscillator. Once that energy is obtained, you will have to use the condition that delta E is equal to 0. So we will have E here, and then we will be using delta E, because now it will take the longer time, and I'm running out of time right now. So I put it on the shoulders of the students that they will solve this problem from here. So what they will do is that once the final total expected energy for this harmonic oscillator comes out, what you will do is you will use the variational condition that delta E is equal to 0. By doing that, you will be calculating beta. And once you calculate the beta, you will reinstate the value of beta in your energy, and you will obtain the ground state energy of this harmonic oscillator. So I would like to stop here, because now it doesn't seem to have any kind of hammers in it. It's all plausible, it's all simple, and it can be done to come up with the ground state energy of the harmonic oscillator.